Let me begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class. Just ask you to bless our work today. Help us to glorify what we do and understand a little bit more about vector fields and conservation energy and all that, Lord. I pray, Lord Jesus. Amen. All right, so yeah.
Trump did the executive order.
Yeah, we have to do the party.
So,
what's the source here? CNN. And I want a reputable source. Oh, that. I'm just kidding. Oh, yeah, I saw that. I was like, what is this? There you go.
thank you.
So yes, you guys are owed a party. It is true. It is true. I mean, at least it appears to be true. The Department of Education, the days are numbered. We can only hope. Now, so you do want to capitalize on that party before more news comes out, and it's kind of like, I understand. But on the surface of things, it does appear that the Department of Education shall soon be no more, at least for the moment. And I don't know. Okay, so I want to talk about integral curves. To vector fields. Just a little bit more. We'll maybe do an example here. So, given your vector field, which let's say has P and Q components, if you have f of r of t is equal to dr dt, then t maps to r of t describes an integral curve. Or if you like, a flow line of the vector field, right? So what are we trying to do? We're trying to, our mission, should we choose to accept it, is to solve, so if we have r is equal to x comma y, then we're up against, dr dt, of course, is dx dt, dy dt. And so what I'd like to solve is dx dt equals to p and dy dt equals to q, right? And it'd be nice if I could do it for like an arbitrary point too, that would be nice. If r, let's say r of 0 is equal to x naught y naught, then this integral curve flows through the point x naught y naught, right? Okay, so let me give us a specific example to work on. Example 1. We could have the vector field equal to, let's just keep it real simple, x minus y. All right. So this vector field is a variable vector field, right? And if we want to find the integral curves to this, what do we got to do? We got to solve. What do we got to solve? I think we can solve this one. This one, we wouldn't even need to get much out of our bag of tricks for this one. Like this we could have solved early on. This is dx dt equals to minus x, dy dt equals to minus y, right? So if I integrate this tells me what? I mean, use separation of variables, use whatever method you want to use. Lambda equals to minus 1 apparently, right? Both of these, actually, right? Both of these are just lambda equals to minus 1 if you think of it as a constant coefficient problem, right? So I can write down the solution immediately. X is equal to x naught e to the minus t. Y is equal to y naught e to the minus t. And you can check, if I look at r of t equal to x naught e to the minus t, y naught e to the minus t. This has r of 0 equals to x naught y naught, right? And there you go. We found the flow of this vector field through the point x naught y naught, that being an arbitrary point, right? What is this? Can you recognize what we're looking at here? This is e to the minus t times x naught y naught. Now I can't always draw the picture, but this one I can draw. You know? If this point is x naught y naught, what's going on? What happens as time goes to infinity here? What are we doing? Right? We're going like this, right? So here is, up here would be like time less than 0. Down here is time greater than 0. The dot is time equals to 0, right? But this point is arbitrary, right? So all of the flow lines to this vector field are what? They're just, I mean, draw as many of them as you want, but the point is that they're all lines through the origin, not through the origin, right? They're not lines through the origin. Actually, the flow lines here are what? They're rays, right? Terminating at the origin. What's the significance? So like the origin is really different than any other point, isn't it? Because the origin is the one place where we don't really have a ray going through it. If our initial condition is the origin, we just sit there, right? So the origin's like a special point here. It's what's called a critical point. The origin is a critical point for this vector field. In fact, the origin is what we might call stable attractor. You know, for F. I don't know, it's a stable attractor. I'm not sure what for I should say, but it's, you know, all the solutions are flowing into that one critical point, yeah? Example 2. What if we're up against the vector field F equals to, oh, I don't know, minus y comma x. In this case, we're trying to solve dx dt equals to minus y and dy dt equals to x. Now, of course, we could use a matrix technique, and we could do that, but we don't really need to here, right? There's a simpler kind of sneaky way to solve this system, right? Like the whole point of the eigenvector technique and everything is to uncouple the coupled differential equations. But these are sufficiently simple. We can just use an ad hoc approach, right? What's the simple way to solve these? How about this? dx dt. Well, you really have ddt of what? X is what? dy dt, right? So I can substitute the second equation into the first. Yeah? And that's super nice because then we're looking at y prime prime plus y equals to 0. We know how to solve that, right? We can solve this. This is solution is c1 cos t plus c2 sine t, right? Then what? Again, our problem is to find the flow lines to this vector field. Okay, that's what we're doing. What's x then? X is dy dt. So x is minus c1 sine t plus c2 cos t, right? But I think it's probably a better move for us to use a little bit of trigonometry here and say, well, we're going to write the solution y is equal to, let's say, y naught cosine of t. All right. I can do that. I want y to be equal to y naught at time 0, so I should write that, right? And then if I do that, let's see here. I may need to do more. And maybe I need plus x naught sine t, maybe? I'm not sure. We'll find out. This is a guess. Right. Actually, let me be less weird. I'm just guessing the answer. Let me derive it instead. Yeah? What do I want right now? The C1, C2 formulas above are general, right? So we can solve those for the desired x naught, y naught. So let's do that. So I want x of 0 to be x naught. I want y of 0 to be y naught. Right? On the flip side, those are equal to what? Well, x of 0 is what? Minus, well, no, x of 0 is just c2. Yeah? If I plug 0 into this, I get sine of 0, which is 0. Cosine of 0 is 1. Plugging 0 into the y formula gives me c1. Oh, okay, so therefore what? Apparently y is equal to y naught cosine t plus x naught sine t, and x is equal to minus y naught sine t plus x naught cos t. So these are parametric formulas for the flow line. Let me rewrite that a little bit more as a parametric thing, like r of t is what? R of t is equal to, we got x naught cos t minus y naught sine t, comma, x naught sine t plus y naught cos t. All right. Any questions? So that would give me a curve which goes through the point x naught, y naught. Do you guys know what this curve is? It is a circle. I don't know. I mean, that's a good intuition you have. Why do you think it's a circle? Just because it's got sines and cosines, or?
The rays.
The rays.
And the sines and cosines.
Huh. Oh, are you saying that this vector field's perpendicular to the last one?
Yeah.
So its flow lines must be perpendicular to the previous one's flow lines? That's very good. That's the way we could think. And fair enough. The orthogonal trajectories to these rays are circles. That's true. Interesting. I hadn't thought of it that way. I mean, in terms of just straight algebra, I think we can show that if this is x and this is y, right? If we do x minus x naught squared plus y minus y naught squared, we're going to be able to show that is equal to x naught squared plus y naught squared. I think. Oh, my bad. We should be able to show, no, that's not right. We should be able to show x squared plus y squared is equal to that. That should be, we should be able to show that, I'm pretty sure. And if you take a step back and just look at the algebra here, if we square the x, right, what happens is you get an x naught squared cosine squared, right, from the x squared, and you get an x naught squared sine squared from the y squared. Those together give me an x naught squared. Likewise, I get a y naught squared sine squared from squaring of x, and I get a y naught squared cosine squared from the squaring of y. Those add together and give me the y naught squared. The cross terms, on the other hand, I've got a minus 2x naught y naught sine t cosine t, and over here I've got a plus 2x naught y naught sine t cosine t. Those cancel in this summation. Therefore, this is how it works out, which is not surprising because what he said geometrically is evident. That vector field is perpendicular to that one if you take the dot products of 0. And geometrically, it does stand to reason that a perpendicular, everywhere perpendicular vector field, it does seem like it should have everywhere perpendicular flow lines. Very good. And of course, the flow lines I can graph. You know, they're just concentric circles. You know, and which direction does the curve go? We can kind of figure it out. Like, check out what happens when I plug in f of 0, 1. What happens there? My bad, f of 1, 0. That's what I want to check. I get what? I get minus 0, comma 1, right? Let me draw that in green. So that points up, right? So if that was like here, we're talking about this being the direction of the vector field, right? The vector field looks like that there. And so these curves are going to be oriented in this sense, which is to say they are going to be counterclockwise, right? Counterclockwise. And if I was to plot more of the vector, well, the thing that makes flow lines interesting is flow lines give you a picture of what the vector field looks like, right? Without actually having to draw dozens and dozens of little arrows, right? Like this tells me that if I was to picture the vector field, it would be looking like, right? But we don't need to draw all these pesky, we don't have to like draw the vector field in that sense. We can just draw some representative flow lines, right? So how about this one? What's the one place that's different than the other places? The origin again, right? And that is exactly where this vector field has a critical point. The vector field 0 at the origin. Something funny happens there in terms of the geometry of the flow lines. Yeah? All right, so another example could be something like this. Let's say x squared minus y squared times y minus 2 x minus y times x minus 3. All right, so to find the flow lines here, we'd have to solve dx dt is x squared minus y squared times y minus 2, and dy dt is equal to x minus y times x minus 3, right? You guys ready? I suggest we don't solve these, right? Like, these are coupled nonlinear. I don't see it going well for us. Now, I mean, admittedly, if I adopted a Cartesian approach, right, there is hope. There is hope for this business that we did earlier in the course, right? Like you could try this out, and that might even be the you might have success with this. Maybe. I don't know. I'll write it down. Right? Maybe there's hope for this because this cancels, right? But still, even I mean, I don't, you know, that looks troublesome, yeah? My question though, you guys, what are the critical points for this vector field? Where is it? In other words, where is this vector field 0? That's what defines a critical point for the vector field. Where would this guy be 0?
For x equals 3.
Yeah, we expect critical points. Let me. You said, what did you say?
X equals 3.
X equals to 3. A point, though. It's got to be a pair of things. You need critical point has both. We need both dx dt and dy dt 0. Right? So we need r of that, whatever, you know. Okay, so we need both of those to be 0. X, okay, so you say x equals to 3 and y equals to what? 2? Yeah, if we have x equals to 3 and y equals to 2, that works. Right?
Would 3 also work?
3 would also work. What else would also work?
Any similar pair.
4, right? 5, pi, whatever, right? Anything of the form x comma x is critical point. So this particular vector field has infinitely many critical points. There's a critical point that, you know, any place where y is equal to x, that makes both this and that 0. So that would constitute a critical point. So this has got this like isolated critical point at 3, 2, and then it's got this whole family of critical points at y equals to x. Now I have no idea what the solutions to this thing look like, or even what this vector field looks like, but I do know that we have a resource that we can use to visualize it without much trouble. We can use p-plane, right? P-plane will let us look at this vector field, and we'll see what the nature of the solutions are by these points. You guys can start me out there and be good. Once my computer comes back to life. Come on. Computer. All right. Come on. You can do it. All right. All right. Are you guys excited about the next homework? No. I think the next homework might be easier. You're like, you always say that. Well, the next homework is easier once you understand it. That much is true. You're welcome. All right. Let us take a look. Yes, I'm doubly attending to attendance today. You guys are happy. Oakley dokley. Here we go. Let me see if I can find us our exciting p-plane. I like the one that's hosted by the University of Arkansas here. You know, There's various websites. All right, so you guys are going to have to help me out. What was our dx dt equal to? What was it, x squared?
X squared minus y squared times y minus 2.
Times, notice I'm using the like ASCII math, x caret 2, y to the caret 2. And then we had what, x minus y, was it?
Times x minus 3.
Times x minus 3. It was x minus y though, right?
Yeah.
All right, here we go. Let's get nuts. Whoa. And so I find that the arrow length is distracting. So let's turn off the variable length arrows. All right. And then we'll have to graph it again. You can kind of see something funny is going on right along the y equals x line, right? You see that? Something funny is going on there. All right, I will eventually find my laser. Ah, found it. So if you look right here, something funny is going on. And where was the other critical point was where? So let me just start, I'm just start clicking. Clickety, clickety, clickety. So here's what the flow lines look like to this vector field. These are the flow lines of the vector field that we're looking at the moment. And I think, so this is a grid. The way this is 1, 2, 3, 1, 2. So this is 3, 2, which was our isolated critical point. What's going on here? We've got someone's going like that, other one's going like that. What's the situation here? The solutions kind of get hung up on the line y equals x, right? Because it's numerically, well, the vector field stops there, right? So like the numerical method they're using to generate these flow lines, it gets hung up on critical points, yeah? So basically all these solutions are stopping at that, you know, at that point. Anyway, so what's the situation here? What do you guys think? As you can see, if you look at the little arrows, you can kind of see. So if you start here, you could flow off that way forever and ever, right? On the other hand, you could flow in over here. You flow off over there. You flow in over there. What kind of point is this? It's a critical point, right? But it's not a stable equilibria. This is like a saddle point, right? This is something like that. All right, so just trying to show you guys a little bit of how we can visualize vector fields using p-plane. Ooh, there's something interesting happening there, isn't there? Look at that. What is that thing? I bet if we were to study concavity of solutions, we'd find something interesting. What is that? Why is there something there? What is that? Where is that?
That would be point 2, right?
Is it? 3 minus 3? Three minus 3. 3. Yeah, 3 minus 3 makes this 0 and that 0. That's right, that's another critical point. We missed it. Yeah? 3 minus 3 is another critical point. We missed it with the algebra, but the p-plane, if we're just willing to look, showed it to us. It's right there. And that looks like maybe some kind of, that's actually, believe it or not, notice all of these solutions are doing what? They're all flowing into it, actually. If you look at it, this is a stable spiral. All the solutions are getting sucked into that point. It's a stable spiral. If we were to, and I'm not going to do this, but if we were to approximate the defining differential equation, if we were to linearize it, all right, and replace that with a linear system, the best linear approximation to that solution, close to this point right here, what we'd find is that it had like an eigenvector with a complex eigenvalue with a negative real part. And so the solutions would look like e to the minus t times the cosine and sine with a vector, and that would get sucked into that point. Like, you do that kind of thing. So there is a whole section in your book on almost linear systems that develops these ideas in more generality than I test on here or anything. All right, let me put this away. So we need to talk about physics now. And let's see here. So we need to talk about energy and force and all that. You guys remember energy and force? What was the deal with the net force? What did the net force solve in physics 231? No one remembers? F equals what? MA, right? F equals MA for the net force, right? Not for any old force, but for the net force, F equals MA. And so let me just take you guys, walk down memory lane here for a minute. If we have F as the net force, then F is equal to m, the mass, times dv dt, right? Yeah. And we can calculate the work done by the net force. That's the integral along a curve of f dot dr. Now, that curve, we're imagining going from, say, a point, say, P1 over here to P2. Right, this is my curve. And we calculate the work done by integrating from time 1 to time 2 of f of r of t dot dr dt. This is the definition of work, right? But if you look at this, if we're talking about the net force, we're also looking at the integral from t1 to t2 of m times dv dt dot what? Well, what is this? What's dr dt? Well, dr dt is the velocity, right? So we're really doing m dv dt dot v dt, all right? And the thing is, if you tilt your head and squint, you can see that that is in fact the integral from t1 to t2 of the total derivative of 1/2 m v dot v. Now that is by no means a trivial step. This thing I did right here, if you like, is the following identity. The derivative of v dot v is dv dt dot v plus v dot dv dt by the product rule for the dot product, which is, of course, twice dv dt dot v, right? So I can trade this here dv dt dot v for that. That's just an identity of the calculus of paths. But on the other hand, we also know that the integral of a total derivative by the fundamental theorem of calculus is what? We've got, 1/2 m, and this is 1/2 mv squared, right? 1/2 mv squared evaluated from, v at time 1 to v at time 2. In other words, we have 1/2 mv2 squared minus 1/2 mv1 squared. You may recognize this as the change in the kinetic energy, right? This is the work energy theorem, right? So the work energy theorem holds as long as we're talking about the net force, right? And we do need the mass to be constant as well. If mass was not constant, then I'd have to think harder about all this, for sure. But then, remember, we also talk about physics a lot about conservative forces, right? What makes a force conservative? What's the definition of a conservative force? I'll remind you. F is conservative on U. Well, let's not say U. Let's say S, a subset of Rn. If and only if F is equal to minus the gradient of U on S. We call U the potential energy function for F, right? And I said that is a misstatement. It is not the potential energy function. It is a potential energy function, because the potential energy is by no means unique, right? You have a choice of where you make potential energy 0, and it doesn't have to be. It's not there's no definition. There's a freedom here. So this is a conservative vector field. So if this is the case, what happens if we calculate the work done by a conservative vector field? Same curve, same setup. We have the integral of minus nabla u, right? Minus nabla. I'll bring the minus outside. Dot dr, right, over the curve. But you will remember that the line integral of the gradient, by the fundamental theorem of calculus for line integrals that you guys should remember from calculus 3, this is minus u of the ending point, minus, I'll factor it out minus there, u of the initial point, right? In other words, it's minus the change in the potential energy, right? And so when you put these two things together, what do we have? Put these two things together. If the net force is a conservative force, right, we can define energy as E of, let's say, R comma V, and it's 1/2 mv squared plus u of r. This is the total mechanical energy. And when we look at these two things I have on this board, we get that the total mechanical energy is what? It is conserved, right? It does not change with time, provided that the net force is a conservative force. Yeah? So that's interesting, obviously. And the question then is, which forces are actually conservative? How do we characterize conservative forces? You know, do you guys remember what makes a conservative force conservative? Do you guys remember there's like 4 competing criteria, one of which I already written on the board, namely that there's a potential energy function whose gradient times minus gives you the force. Path independence is another, very good. Path independence, very good, yeah. So we have the theorem. If F is vector field on S subset of Rn, then the following are equivalent. Number 1, F is equal to minus the gradient of a potential energy function on S, right? So my number 1 here is exactly the definition of conservative force. All right? It's number 1. What's number 2? How about the path independence that you just mentioned? That would be good. It's a good one. path independence. Very good. What does path independence mean? Path independence. What we mean by that is given two coterminal paths, C1 and C2 in S, the work done by the force along C1 is equal to the work done along by the force along C2, right? The line integral of F along C1 is equal to the line integral along F of C2. Along C2 of F, yeah. So yeah, that's another equivalent condition. 3, how about this? The integral around any loop of F dot dr is equal to 0, right? So this is for any loop. For all loops in S. All right. What's the fourth one? This one's special. This one's special. Assuming n equals to 3 and S simply connected, all right, simply to say that S is simply connected means that any loop that we can take in S, it can be smoothly deformed to a point. All right. So, for example, if I take R3 and I throw out an axis, like I take R3 and I remove the z-axis, this would not be simply connected because I would not be able to get the, if the loop was around the z-axis, I couldn't smoothly deform it to a point, right? There's something missing there. In n equals 2, if you take the plane and you delete the origin, that's not simply connected because you get hung up on the point missing at the origin. But in this context, we can also add the curl of F is equal to 0. That is a sufficient condition to imply the existence of a potential energy function. All right? How do these ideas go together? I mean, like, I probably spend about an hour and a half in Calculus 3 proving the equivalence of these ideas, all right? Some parts of it are just drawing pictures, you know? Like, essentially the equivalence of 2 and 3 just stems from the fact that if you take a loop, you could just, like, draw it as a pair of paths that are coterminal, you know? So, like, if you think about the loop, right? If I pick 2 points on the loop, I could call the upper one like C1 and the lower one C2. So my loop I could think of as being like C1 unioned with minus C2, right? So if you think about that, if I have the integral around a loop is 0, it means that I have the integral along the union of C1 and union minus C2 being 0. But the way the line integral works is if you take a path union with another path like this, then the properties of the line integral said that that's the integral of C1 minus the integral along C2. All right. The minus here on C2 says that it's oriented the opposite way. So like a picture of minus C2 here would be this, all right? So this identity basically shows you why we have an equivalence between 2 and 3, right? It's somewhat technical, why path independence implies 1, but 2 implies 1 stems from fact you can write u at r equals to minus the integral from some potential point r naught to r of f dot dot dr. You can differentiate this, and I'm not going to do that, but you can differentiate this and show that the gradient is equal to minus f. So in fact, and the reason that this integral makes sense, in part, is the path independence. Path independence says that I can meaningfully write the integral from r naught to r. It doesn't matter which path I pick from r naught to r. And when you actually go through this derivation, you carefully choose paths which are just horizontal in their approach or just vertical in their approach to the limiting point, and that makes contact with the gradient through the fundamental theorem of calculus. It's always fundamental theorem of calculus when you get to the end of it. This formula we actually use in physics 2. Do you guys know where? What's the formula for voltage in physics 2? Do you guys remember? For those of you who've actually taken physics 2, and that would not be all of you, or maybe any of you, I don't know. Anybody taken physics 232? Do you remember this formula? The voltage is minus the integral from the potential to r of E dot dr. That's exactly this. What's the difference is that voltage is what? Voltage is potential energy per charge. So if you take that equation, you multiply by Q, then you've got the potential energy and the integral of a force. But that's a particular instance of this mathematics. We can integrate the force, or in this case, the electric field, to get the potential. Again, this is potential in the sense of physics 232, which is not potential energy, but rather voltage, which is potential energy per unit charge. Let me erase this from the record, as I try not to do that in here. But what's the deal with this one? How does this get thrown in the mix? How does this relate to these? Do you guys know? Remember at the end of Calc 3, we talk about a theorem. What was that theorem? Remember? Stokes' theorem? Stokes' theorem? That thing that happened at the very end of Calculus 3 and then you forgot about it? So it is that the flux of the curl, so f curl of f dot ds vector is equal to what? So this is over some let me say some surface. I need some letter for it. I already used S for something else. We'll call the surface Q. Why not? That's bizarre, but I'll allow it. So the flux over Q of the curl, Stokes' theorem says that that's equal to the integral over the boundary of Q of f dot dr, right? Okay, so what does this mean? And the thing is, this applies as long as Q is simply connected. All right, so if you think about, you got this space, right? And then you can take this, this membrane Q, some surface in the 3 dimensions, let's say. So S is some sort of blobbish region in R3, right? And Q is a membrane inside that region that we're talking about, S, whatever that is. The point is, the curl of F is 0 on Q, which means that the integral around the boundary of Q is 0, right? But the thing is, you can do this for an arbitrary loop in S, right? Take an arbitrary loop in S, color in that loop, call that Q. We have the integral around that loop is 0. Therefore, we're back to like 1, 2, and 3. We have conservative force. Yeah? Now, part 4, when we look at n equals to 2, what happens with n equals to 2 here for 4? Sorry, I didn't make any examples today that we needed to use eigenvectors for. I'm sorry. I wasn't trying to avoid eigenvectors. My examples were too simple. But I think I think the problems in your homework might need eigenvectors, maybe. Maybe at the start of the next mission. So that we still know those things and we can use them. But if we think about in the n equals 2 case, so my vector f would look like, we could think of the p equals 2, n equals 2 case, we can think of this as subcase, right, of n equals 3, where my vector field has just 0 z component, right? What's the curl look like of a vector which has 0 z component? What's the curl? What's the curl of f here? Remember, generally speaking, it's partial y of f3 minus partial z of f2, partial z of f1 minus partial x of f3, partial x of f2 minus partial y of f1, which in my case, f1 is p, f2 is q, f3 be 0. And notice that p and q, we're assuming only depend on where? To make this two-dimensional, p and q have to be what? Only depend on what? X and y, very good. Which means all of my z derivatives are nothing. So this curl just breaks down to 0, 0, and this guy is partial xq minus partial yp. So this being 0 is equivalent to the condition that partial xq equals to partial yp. This, we remember, is the closed condition for what? This is the closed condition for the differential equation p dx plus q dy equals to 0, right? So for a two-dimensional vector field, there's some kind of connection between exact equations and conservative vector fields. Yeah? If we can solve one, we can solve the other. Let me make that explicit here. So here's a theorem. If f equals to p comma q is conservative, then p dx plus q dy equals to 0 is an exact equation. Moreover, u of x comma y equals to a constant solves star, where u is the potential energy. Let me show you a concrete example of this. Let's see here. So, what, example 4 maybe? I don't know. Suppose I have f is equal to, say, x plus, y plus 1, comma, x plus 2. So here I have, this is minus the gradient of what? I look at this, I go, oh, well, I can just put xy. Xy, really minus xy, right? Minus xy, minus x, minus 2y. I think I'll do it. If we calculate the gradient of this, what do we get? I'm checking my work, guys. I'm an idiot. What's the partial derivative of xy with respect to x? It is y. And on the other hand, partial derivative with respect to y of xy is x. It's got minus x over here. Oopsie. Oopsie doopsies. Minus 2. Multiply the minus through. Yay. All right. So indeed, the potential energy I pulled out of a hat. Thus, my potential energy for F is U of xy equal to minus xy minus x minus 2y. And you know what? I don't know, like you guys, I personally don't like the minus in this formula. Like you could put a plus or minus in my theorem. All right, if that's okay with you guys, plus or minus there. So in view of the plus or minus there, the solution, if we look at like big F, oh man, unfortunate letter. I usually use big F, I guess use G this time. Big G of xy equal to xy plus x plus 2y has dg equal to what? Take the total differential of big G there, and we get that, right? So this is equal to 0 for what? For big G of xy equal to a constant. That is, you know, xy plus x plus 2y equals to a constant solves, you know, y plus 1 dx plus x plus 2 dy equals to 0, right? It's a 2-for. If you can find the potential energy for a conservative vector field, you've also solved a corresponding exact differential equation if we're talking about the two-dimensional problem. These problems are linked. It's the same math. So, do you guys remember how we found the potential energy, or the potential, if you will, for a vector field? Back in Calc 3, what did we do? So I think the first problem I have in your homework, or at least one of the first ones, is I just give you some vector fields and ask whether or not they're conservative. Yeah? So how do you figure that out? If I give you vector fields and ask you, are they conservative or not, what would you do? I mean, one thing you could do is calculate the curl, right? And if the curl is 0, does that mean the vector field's not conservative? So if the curl is 0, that means the vector field's conservative. Is that right? How about this one? If we look at example 5, so here's f. We'll do f of x, y, z equal to minus y over x squared plus y squared, x over x squared plus y squared, and I don't know, z.